Now that we know how to identify nearest neighbors, how do we determine the value of k in KNN? At one extreme, we can select k equal to 1, which only uses the nearest neighbor to help us make the prediction. At the other extreme, we can select k equal to n on the number of observations in the dataset. Then the entire dataset is used to make the prediction. Different values of k will lead to sometimes drastically different predictions. How do we know the value of the optimal k? Remember that in supervised data mining, we have a secret weapon called data partitioning. Data partitioning not only helps us evaluate the predictive performance of the model, but helps us optimize the complexity of the model as well. To find the optimal k, we will try a range of values for k, for example, from k equal to 1 to k equal to 20, and choose the value of k that produces the lowest prediction error in the validation dataset. It works like this. We start with k equal to 1. For each validation data case, we identify one nearest neighbor of the case from the training dataset, and then use the nearest neighbor to make the prediction of the target variable. At the end, we compare the predicted target values to the actual target values in the validation dataset to assess the performance of the prediction. Then we move on to k equal to 2 and identify two nearest neighbors of each validation data case from the training dataset to make the prediction for the target variable, and then assess the predicted performance for k equal to 2. We continue this process until we have reached the largest value of k we specified. We then compare the predictive performance of each value of k to select the lowest value of k with the best predictive performance. As you can see from this process, the validation dataset is involved in selecting the best k or the best model. Therefore, a separate dataset, the test dataset, is often needed to get an assessment of how the selected KNN model would perform on unseen data. Data mining software products such as Analytics Solver or SAS Enterprise Miner tend to use this approach. Alternatively, there is another approach that does not involve a test dataset. Instead of using the validation dataset to find the predictive performance for each value of k, we can employ the k-fold cross-validation method on the training dataset to identify the value of k that produces the best average predictive performance. The k-fold cross-validation approach would partition the training data into k subsets. For example, if we use the 10-fold cross-validation, then we will partition the data into 10 subsets, and use k-1 or 9 subsets to perform the analysis, and leave one subset as the validation dataset. Each time the analysis is performed on the training data, a different subset is left out to be the validation dataset. The performance of the model is evaluated by averaging the performance measures across all k left out subsets. The k-fold cross-validation approach is less sensitive to the effect of data partitioning compared to the approach discussed earlier. Therefore, it is sometimes preferred. In addition, it only requires a two-way partitioning rather than a three-way partitioning that was used in the previous approach. Data mining software products such as R tend to use this approach. No matter which approach you use to identify the optimal k, There are a couple of things you need to know about the value of k. A low value of k, for example, k equal to 1, 2, or 3, tend to capture the local structure of the data, which is an important advantage of the KNN technique. Local structures refer to the uniqueness of the cases and are often difficult to capture using traditional statistics techniques. However, low values of k also tend to capture the noise in the data that cannot be generalized to new datasets. On the other hand, high values of k, for example, k equal to 20, 25, or 30, tend to provide more smoothing of the prediction to get rid of the noise in the data. But at the same time, it can also lose important local structures of the data. Therefore, choosing the optimal k is a combination of both science and art. How do we combine the information from the nearest neighbors to make predictions? Let's first look at using KNN for classification problems, because classification problems are the predominant problems solved by KNN. After the selected number of nearest neighbors in the training dataset are identified, we can use a majority decision rule to classify the new cases. In our example of credit card application that was discussed before, 2 out of the 3 nearest neighbors paid their credit card debt on time. Using the majority decision rule, we would consider the new applicant a desirable customer and classify the application into the approved class. Using the majority decision rule is equivalent to using the cutoff value of 0.5 for binary class problem. If the majority decision rule is used, it makes sense to use an odd number of k, as this would avoid the situation where a tie is observed. In many real-life cases, a sliding cutoff value may be more appropriate. If you use a cutoff value that is lower, then we are classifying more cases into the target or success class. And if you use a cutoff value that is higher, then we are classifying less cases into the target or success class. Determining the cutoff value is again both a science and art. It will depend on many factors, including misclassification costs, overall probability of cases belonging to the target class, and etc. If we use a sliding cutoff value, then we need to obtain the probability of the case belonging to the target class. The probability can be computed by dividing the number of nearest neighbors that belong to the target class by the total number of nearest neighbors. For example, in our credit card application example, if identifying potential credit card customers who are likely to be delinquent is the goal, then delinquent would be the target or success class, since one of the 3 nearest neighbors is delinquent. The new applicant will have the probability of 1 divided by 3, or 0.33 probability of being delinquent. A general rule of thumb is to use the overall probability of cases belonging to the target class as the cutoff value if no other information is available. Since there are 3 delinquent customers among the 10 customers, the overall probability of a customer being delinquent on payment is 3 divided by 10, or 0.3. So using 0.3 as our cutoff value, the new customer would be considered to have a higher probability of being delinquent on payments, because his or her probability is greater than the cutoff value of 0.3. Therefore, we will classify the new applicant into the delinquent class and deny the application. The performance measures for KNN classification are the same as other classification problems. Misclassification rate, sensitivity, specificity, cumulative lift chart, decile-wise lift chart, and RLC curve are all useful to determining the model's predicted performance. Although the use of KNN for prediction problem is less common, we'll discuss the concepts behind it here as well. It uses the same similarity measures as in classification problems to identify the nearest neighbors, but it differs in how it evaluates model performance and how to arrive at a prediction. The prediction is usually computed as the average value of the nearest neighbor's numeric target variable. For example, if we use KNN to predict the selling price of a used vehicle, we can identify k nearest neighbors of the used vehicle in the training dataset and average the selling prices to predict the price for the car. A more sophisticated approach would be to use a weighted average, with the weight decreasing with increasing distance from the case being predicted. For example, the most similar used vehicle to ours would be given the highest weight, whereas the farthest near neighbor would be given the lowest weight, to arrive at a weighted average of the selling price of our used vehicle. The performance measures will be consistent with other prediction problems. The root mean square error, mean absolute error, or mean absolute percentage error are often used to help select the optimal K, as well as assessing the model performance on new datasets. So to summarize, K nearest neighbors is a widely used data-driven technique for both classification and prediction applications. The technique identifies a number of cases in the training dataset that are most similar or closest to the new case to determine its predicted outcome. Similarity measures such as Euclidean distance are used to identify nearest neighbors, and either the validation dataset or a k-fold cross-validation technique can be used to determine the optimal value of k. For classification, the technique uses either the majority rule or compares the probability of the case belonging to the target or success class to a cutoff value to determine the class membership of the new case. For prediction, either a simple average or weighted average of the numeric values of the target variable for the nearest neighbors is used as the prediction. Now that we understand the concepts of the KNN technique, let's apply it to a practical problem. In this case, a fitness center, 24/7 fitness center, is trying to predict which of its open house visitors are likely to sign up for an annual gym membership. It has a data set that has data on past open house attendees. The variables include their age, income, number of hours spent exercising every week, and whether they end up enrolling in an annual membership or not. The fitness center manager, Janet, would like to develop a classification model to predict whether a potential gym member will purchase an annual membership based on his or her age, income, and weekly exercise routine. In addition, Janet would like to use the classification model to score the 23 potential customers who attended the last open house.